the boundary conditions that are on one side, the electric potential is set to 0, and on the other side it is set to minus the built-in potential. And we observed that if we take the solution, that is the values of the electric potential at each point in the semiconductor, and then use the equilibrium expressions of the concentrations of electrons and holes in the exponential form, because we are assuming the non-degeneracy condition, then the concentration of the electrons is the exponential of phi. So if we draw a graph in which instead of the concentration n, we use the logarithm of n, we expect to obtain a curve that is similar to this apart from some constant. And if we make another graph describing the whole concentration, again in a logarithmic scale, then we find the behavior again of the electric potential with the minus. So it is flipped top down. We shall see it in a second in the next page. So if you look at the left part of the page, you see that the concentration of the electrons is reproducing the form of the electric potential apart from constants, because this is a logarithmic scale. So the vertical scale is logarithmic. The left value of the concentration of the electrons, you remember, is called NP0. It is the asymptotic value of the equilibrium concentration of the electrons in the P region. And that on the right is called NN0. Similarly, we have a curve describing the concentration of holes. Of course, it is larger on the left because we have the P zone in the left part. And we use the symbols PP0 on the left and PN0 on the right. So let's try to make to fix the numbers, okay? We take, as before, a constant concentration of acceptors in the P zone equal to 10 to the 16th atoms per cubic centimeter. And on the other side, we take ND equal to 10 to the 15th atoms per cubic centimeter. Then we take the room temperature, so we remember that the intrinsic concentration in silicon is in the range of 10 to the 10th per cubic centimeters, okay? Now, you also remember that PP0 is practically equal to NA. So if you look at the left part of the figure, the upper left part, the constant value PP0 on the left is 10 to the 16th. The constant value N0 on the right is 10 to the 15th, because it is practically equal to ND. So you see that N0 in the figure is lower than PP0, and the difference in the vertical position is equal to a factor of 10. So that unit, that difference, is equivalent to a factor of 10. Then we calculate Pn0, that is the minority carrier concentration in the N region, and this is obviously equal to Ni squared divided by Nd. That makes 10 to the 20th divided by 10 to the 15th, sorry. So we have 10 to the 5th. So Pn0 in the figure is 10 to the 5th. It is 10 orders of magnitude smaller than nn0, because nn0 is 10 to the 15th and Pn0 is 10 to the 5th. And finally, we calculate on the left np0, that is the minority carrier concentration in the P region. And that comes to be Ni squared over Na, and that makes 10 to the 4th, because it is 10 to the 20th divided by 10 to the 16th, okay? So NP0 is 12 orders of magnitude smaller than PP0, okay? Obviously, in a log scale, all these values are visible. However, if you now look at the right-hand side of the figure, you see the same graphs, but in a linear scale, okay? So PP0 is the largest. The constant value of PP0 is, as you remember, 10 to the 16th. Then you go to the right, you find NN0. That is 10 to the 15th, so it is 10 times lower than PP0. So in a linear scale, it is much below with respect to PP0. Then the minority carrier concentrations NP0 and PN0 are practically invisible because they are orders and orders of magnitude smaller than the corresponding majority carrier. So you see, if you start from any point on the left of O minus, so if you start in the neutral region of the p-type, essentially you have PP0 is the dominant concentration, so the holes are dominant, okay? But then you enter the space charge region in which the concentration of the holes must go from the values on the left, that is majority carriers PP0, to the value on the right, that is minority carriers PN0. So they have to decrease by 11 orders of magnitude, okay? Holes must decrease very much. And this decrease occurs almost immediately when you enter the space charge region. That means that you see the curve, PP0 decays immediately practically to zero very soon when you enter the space charge region. And the same happens for the electrons. If you start from the right of O plus, you have NN0, that is the largest concentration, and then you enter the space charge region, and immediately the concentration of the electrons drops to very low values, okay? In conclusion, we are in the equilibrium situation, okay? In the equilibrium situation, we may state that the mobile charges, that is holes and electrons, have a concentration that is substantially negligible, almost negligible, in the space charge region, that is in the central part of the structure, okay? They dropped almost immediately to very low values. So who is contributing to the charge density in the space charge region? The only possible contributions come from the charges that cannot move. And those are the charges associated to the positively ionized donors atoms and to the negatively ionized acceptor atoms, okay? So where are they? In the abrupt junction, the donor atoms are on the right of the origin. Okay, so if you look at the region between the origin O and the abscissa O plus, that is the boundary of the neutral region on the right. Okay, between O and O plus, that is in the space charge region of the n-type, the only important contribution to the charge density is given by the donor atoms. So you see that there is a formula here at the bottom. When X is in between minus LP and plus LN, you remember LP, LN are the lengths of the space charge region on the p side or the n side. In the space charge region, in the equilibrium condition, the charge density is practically equal to the dopant concentration times the electron charge. And more precisely, when X is positive, that means between O and O plus, this contribution is equal to QND, because on the right of the origin we have only donors. Instead, between minus LP and 0, that is for negative X, the essential contribution to the space charge is given by the acceptors, and you remember they are negative. So it is minus QNA. The question is, do we have a current? Of course we don't, because we are in equilibrium, okay? But if you look at the profiles of the concentrations of holes and electrons, they are not constant. So the concentration of holes goes from a large value pp0 in the p region to a much smaller value pn0 on the right. So in the middle there is a gradient, okay? And you remember that there is a transport phenomenon called diffusion, such that the particles that are able to move go from the regions where the concentration is higher to the regions where the concentration is smaller. So there is a possible contribution to the diffusion term, that is the gradient of the hole concentration in the space charge region, and of course this diffusive process would push the holes from left to right, because there are many holes on the left and not so many on the right. Okay. This flux is not there because it is counterbalanced by the electric field. In fact, if you look at the space charge region, the space charge region on the right part between 0 and O plus is rich in positive charges that are the ionized donors, and on the other side it is rich in negative charges. So we have positive charges on the right, negative charges on the left, so we have a field that goes from right to left. It is oriented from right to left. And of course this field pushes the holes to the left. So diffusion would try to push the holes from left to right. The electric field is pushing the holes from right to left. In the equilibrium conditions, these two actions counterbalance each other exactly, and we have no current. So if you look at the expression of the drift diffusion current density for the holes, you find that remember the field goes from right to left. So it is negative because it points opposite to the orientation of the x-axis. So E is negative, so this term is positive. The diffusive term, again, dP over dx is negative because the hole concentration decreases from left to right. And we have a minus sign, and this term also is positive, and they are equal to each other. So they balance each other exactly, and we don't have any current. Similarly, the concentration of the electrons increases, so the derivative is positive. All this term is positive, the diffusive term. And the drift term is also positive because the field is negative. Okay, so for the same reason, also the electron current globally is zero. So at equilibrium, we have an exact balance of the diffusive and of the drift term. Okay, so far we have neglected the fact that at the end of the p-type region and at the end of the n-type region, we have the contacts. Okay, for the moment we have always assumed that the p-n junction is infinitely long on the right and on the left, but it is not so. There are two contacts, okay? In general, these contacts are made of metal. So when you place a metal attached to a semiconductor, you have discontinuity in the electric potential that we already talked about. It is called the work function difference between the two materials, okay? In principle, it is similar to what happens in the p-n junction. In the p-n junction, you have the same material, for instance, silicon, but the doping type is different. So it is similar to having two different materials attached together. And in fact, in the p-n junction, you have a change in the electric potential, okay? The same happens when you have a junction between a metal and a semiconductor. Again, you have a change in the electric potential. There is one difference, though, that in the metal semiconductor junction, the change in the electric potential occurs in a very, very small region of space. Okay, so in many situations, we can replace the change in the electric potential with the discontinuity. Okay, and this is done in this figure. Okay, if you look at the right hand side, you see that if you keep considering the zero of the electric potential in the neutral region of the n-type, as we did before, okay? So you see this constant line here is the zero of the electric potential, okay? At some point you reach the position of the metal contact. You have discontinuity of the electric potential that in this case it is taken negative, so that when you go from the semiconductor into the metal, the change of the electric potential goes from 0 to some minus some constant that is indicated here with phi mn. So phi stands for the potential, for the electric potential. Mn stands for metal n-type semiconductor. So M is for metal, N is for the n-type semiconductor. The amplitude of this discontinuity depends on the type of doping. First of all, it depends on which semiconductor and which metal are attached together. Then it depends on the type of dopant and also on the concentration of dopant. Okay, so it may be different depending on the situation. On the other side, you see, we are in the equilibrium situation. So we start from the zero that is in the N region on the right, okay? Then we enter the space charge region. So we have the change in the electric potential that in principle we should find by solving the Poisson equation, okay? On the other side, we have a value of the potential that you remember is minus the built-in potential psi. Proceed to the left. We reach the position of the left contact, and then we have another discontinuity. And this discontinuity is different from the other one because this is a p-type semiconductor, okay? However, we assume that the metal with which the left contact is done is the same metal as on the right, okay? So the work function difference is not the same in the two contacts because the semiconductor is different. Here we have phi MP, that means the work function between a metal and a p-type semiconductor, okay? Since we are at the equilibrium, in the equilibrium condition, then there is no voltage applied to the p-n junction. The p-n junction is in equilibrium, so the voltage is zero, the applied voltage is zero. And in fact, you see that the horizontal line related to the potential of the right contact is exactly aligned with the horizontal line describing the potential on the other side, because actually that is the same piece of metal, and the left contact is shorted with the right contact, okay? So this is the situation. Now let's go from left to right, okay? We start again, we start from the left, okay? Then we have this value of the potential. At the discontinuity, we go down by phi MP. Then here we go up by phi 0. And then here we go down again by phi mn. Okay, and we reach the same value of the potential as the one we started from. Okay, so this is like applying the Kirchhoff law for the loops. Okay, and the formula is below. You go down by phi MP. Going down means that you go opposite to the arrow that defines phi MP. Then you go up by psi 0, and then you go along the arrow here by phi mn. So this is the balance relation. It tells you that the built-in potential is equal to the difference phi mp minus phi mn. Okay. Also, you should remember that the two differences in work function depend on the dopant concentration. So if you take another p-n junction with another distribution of dopants, phi mp and phi mn will turn out to be different. Okay. In the upper part of the page, you see the symbol that is used in the PN junction, for the PN junction in circuits. So if you want to draw a circuit and you have a PN junction somewhere, you should use this symbol. You remember the triangle is on the P side and the vertical bar is on the N side. And the symbols I and V also indicate the typical arrangement that is taken to describe the current and the voltage at the contacts of the PN junction. Okay, so whenever possible, we take the arrow describing the current as pointing into the P region, okay, whenever possible. This is the standard way of taking the current, the direction of the current. What does it mean? It means that if the current is given by a positive number, the actual circulation of current is clockwise. If I is negative, the actual circulation of current is counterclockwise. Similarly, this is the arrangement that is typically used for the voltage. So the arrow of the voltage, whenever possible, points to the P contact, okay? So that means that if V is a positive number, the electric potential on the P contact is higher than that on the N contact, and vice versa, okay? So this is it as far as the equilibrium description of the PN junction is concerned, okay? Now we have to go to the non-equilibrium condition and calculate the current of the junction produced by the application of a voltage. You know very well that with this direction of the arrow of the voltage, when V is positive, we talk of direct bias, okay? When V is negative, we say the junction is reverse biased, okay? In both cases, it is in a non-equilibrium condition. So now we have to go to the non-equilibrium condition. And we use some hypotheses that are acceptable to describe the non-equilibrium condition. The hypotheses are that, number one, the contacts are ideal. That means that the ideal contacts are those such that the difference in the work function, that is phi mn, or in the other case, phi mp, do not depend on the current that flows in the structure. Okay, so when we go from the equilibrium to the non-equilibrium situation, phi mn stays the same and phi mp also stays the same. They do not change. So this is hypothesis number one. Hypothesis number two, that also is applicable if the applied voltage is not too large. Okay, the second hypothesis is that even in the non-equilibrium condition, the partitioning of the PN junction into three regions is still feasible. So there is still a central part of the PN junction that is the space charge region, and two lateral parts that are the neutral regions. Okay, so this partitioning is still applicable also in the non-equilibrium condition, provided we are not too far from equilibrium. Okay, so now we shall see two pictures. One picture describes how the shape of the electric potential changes in the direct bias. The other refers to the reverse bias. Okay, qualitatively, you may expect that when we are in a non-equilibrium condition with the direct bias, V is zero at equilibrium, then it will be positive in the direct bias. Positive V means that the potential on the left contact is higher than that on the right contact. So that means that this horizontal line here, that in the equilibrium condition is exactly aligned to this line, okay, this line will go up in the direct bias. Conversely, for V negative, this line will go down, okay? So we still keep the zero of the electric potential in the bulk of the end zone, so far away from the junction, okay, here. And this is always possible because we can always fix the zero of the electric potential where we like, okay? So we keep the zero here. And then you remember for a positive bias, the left side here will go up. For reverse bias, it will go down. And these are the two outcomes, okay? So the upper part is related to the direct bias, positive V, okay? So the thin line is the equilibrium case, the same as the previous page. The thick line is the new case, okay? So we apply V and we push the horizontal line that used to be here at equilibrium, we push it up by the amount V. Now, you remember the other assumption is that the wave functions do not change. So the discontinuity at the contact will stay the same as in the equilibrium case. Then we pass the discontinuity and we go to the right, okay? Now, we assume that a neutral region still exists, okay? So in this region, the potential will be constant, okay? So we have a horizontal line up to the edge of the space charge region. Now, there is one question. When we go from equilibrium to non-equilibrium, do you expect that the extension of the space charge region stays the same, or do you expect that it changes? It changes. In particular, when the PN junction is in the direct bias condition, the space charge region shrinks a little, not that much. So O minus goes a little to the right with respect to equilibrium. O plus goes a little to the left. So the vertical line corresponding to O minus and the equivalent vertical line corresponding to O plus are the actual position after the application of the direct bias, okay? The two external lines, this one and this one, are the two positions that were originally there at equilibrium, okay? So in the description, we have reached O minus, okay? So now we keep it. Then we go on the other side. On the other side, the region, the neutral region of the n-type stays the same. So the potential is a constant and equal to 0 there, okay? And the discontinuity doesn't change. And the horizontal line here does not change with respect to equilibrium, okay? Because we have taken the 0 on this side, okay? So globally, what does it happen? It happens that on the left-hand side, sorry, on the right-hand side, the profile of the potential does not change with respect to equilibrium. On the left, all this part rigidly shifts upwards. And then inside, we must have a continuous connection of the electric potential from the value at O minus to the value at O plus, okay? So if you look at the figure, the drop in the potential, in the electric potential between O minus and O plus, the drop is called psi, okay? You see it's the difference between the value here and the value on the other side. Psi is smaller than psi 0. Psi 0 is the equilibrium, okay? So the potential drop across the p-enzyme, across the space charge region due to the application of a direct bias is such that across the space charge region, the potential difference is smaller. On the other hand, the length of the space charge region is almost the same as in equilibrium. It becomes a little bit smaller, but not that much, okay? So we have a substantial change in the potential drop over more or less the same length. The conclusion is that the electric field will decrease because the decrease in the voltage is significantly more important than in the decrease in the extension L, okay? So we have a smaller electric field, okay? If the electric field becomes smaller with respect to equilibrium, okay, the drift term of the transport equation will become weaker because the field is smaller, okay? Now we have to understand what happens to the diffusive term, and that term does not change because substantially the concentrations of the electrons and holes on the two sides of the space charge region do not change, okay? They are dictated by essentially the dopants. So the concentrations do not change. The extension of space over which the concentration changes from majority to minority is essentially the same. Actually, it is a little bit smaller. So the diffusion will stay the same, or maybe it will increase a little, okay? So the diffusive terms of the transport equation will be dominant because the diffusive part does not change, or it may increase a little bit. Whereas the drift part of the equations becomes weaker, okay? So you remember the two terms balanced each other at equilibrium. They are not balanced anymore, okay? Diffusion prevails. It follows that we shall have an injection of holes from left to right, from the place where there are many to the place where there are not so many. So we shall have a current produced by a flux of holes from left to right, and at the same time, and still due to diffusion, we shall have a flux of electrons from right to left, because electrons are many on the right and fewer on the left. Okay? So we expect a significant current, and the current will flow from left to right, because holes go also from left to right, and they are positive. Electrons go from right to left, but they are negative, so the current associated to them still goes from left to right. Okay, so this is the condition of direct bias. When we go to the lower part of the figure that corresponds to a reverse bias, we have the dual situation. This horizontal line on the left will go down because V is negative. The discontinuity will stay the same. The neutral region, again, will have a constant potential until we reach the edge O minus of the space charge region. Okay. When you apply a reverse bias to a p-n junction, the extension of the space charge region increases. So in this case, L is larger, this L, than in equilibrium, and even more so with respect to the direct bias, okay? So this increase in the extension of the space charge region in reverse bias is significant, okay? It is not a minor thing, okay? On the other side, nothing changes, so you see immediately that in this case, the total drop psi over the space charge region is larger than psi 0, okay? In this case, the electric field obviously increases because we have a larger voltage drop over a region that is also larger, but we shall see the field does increase, in any case, in the space charge region, okay? But this field, although large, will act on a very small number of charges, because you remember from the analysis that we have carried out in the equilibrium condition, the space charge region is almost completely depleted of electrons and holes. So there are some, but not so many. So the strong electric field will act on very poor populations, okay? And when we go from equilibrium to the reverse bias condition, the populations of electrons and holes in the space charge region will become even smaller than in the equilibrium condition, okay? So there is a large field which, however, acts on a very small number of charges. So the conclusion is that in this condition, the current is small, okay? If you go around the loop in a non-equilibrium condition, you again find that the new drop that you call psi plus phi mn plus v, because in this case we have a non-zero value of v, minus phi mp is 0. Okay? But you can recast this equality by collecting the difference phi mp minus phi mn. And then you remember that this difference is equal to psi 0. Okay, so this relation can be written in a shorter form, telling you that the actual drop over the space charge region is equal to the equilibrium value psi 0 minus the applied voltage. So in direct bias, V is positive, so that psi is smaller than psi 0. For a reverse bias, V is negative. So psi is larger than psi 0. Okay. Obviously, we can also indicate psi as the difference in the electric potential between O plus and O minus. This is nothing else than another expression for psi. Okay. One question. We said that in the direct bias, V is positive. Okay. Can we apply a V that is larger than the built-in potential? So if we have a built-in potential of, remember, 0.7 volts, okay, can we apply a positive bias to a junction equal to 2 volts so that psi becomes negative? In principle, we can, okay? But we cannot apply the simplified calculations that we are going to show in the next hour, okay? So in general, when we apply a direct bias to a junction, this direct bias is not so large. Also, if it is too large, the current, as we shall see, depends exponentially on the voltage, so the current will be very large and may damage the junction, okay? So the direct biases should not be too large. The reverse biases can be rather large, okay, unless we push it to the point that we reach the condition of avalanche and we destroy the device, okay? Another issue is that, as we anticipated, the distances LP and LN depend on the applied voltage, okay? They can also be calculated analytically in the reverse bias condition because the analysis is somewhat easier, okay? And this is the important side of the analysis because the change in the space charge region extension is significant only in the reverse bias condition. When we are in the direct bias, the change in LP and LN is not so important. Okay, so it is now 6, so we stop for 10 minutes. And if you have questions, you may send a note by email or in the chat, okay? And we shall resume in 10 minutes. Okay, so we now proceed with the analysis of the p-n junction. And the purpose of the analysis is to calculate the current voltage relation. So we take a steady state situation. We assume that we are applying a voltage that is constant with respect to time, and we want to calculate the corresponding current. Okay, these two figures essentially reproduce by drawings the concept that I was expressing using the other figures. So it is an illustration of the fluxes in the device, okay? And now we perform some calculations, assuming some simplifying hypothesis. First of all, we take a one-dimensional case. So the semiconductor model will be reduced to the one-dimensional form. And we also consider the steady state condition. So there are no dependencies on time. Then we shall assume that the junction can be still be partitioned into the two neutral regions on the sides and the space charged region in the middle. And all this theory goes under the name of Shockley theory, as you can see here written on top of the page. Shockley is the gentleman who first made these calculations. Now, let's start from the general form of the continuity equation. The continuity equation that involves all charges and all current densities, so that the right-hand side is a zero. So we take the time derivative of the charge density plus the divergence of the total current density is zero. If we are in steady state, the time derivative disappears. Then, if you are also in the one-dimensional case, the divergence of J becomes the derivative of J with respect to X. And this is zero because of the continuity equation. So if the derivative of J is with respect to X is zero, that means that J is a constant. On the other hand, you remember the current density in general is the sum of the current density due to the holes, Jp, plus the current density due to the electrons, Jn. And individually, Jp and Jn depend on position. However, the sum does not. So Jp is a function of x, Jn is a function of x, but the sum of these two functions is a constant. This constant is not known for the moment. We don't know it yet, okay? But we know that the sum is a constant at each position, is the same constant at each position x in the p-n junction. This is useful because this result tells you that if you succeed in calculating the total current density J in one position, then it will be the same in all other positions. Okay. Now we consider the continuity equations for electrons and holes separately. And we assume that there is only one type of generation recombination phenomena, that is the thermal ones. You remember the function that we call U, or U Shockley Reed Hall, okay? So we put all the other contributions to generation recombination to 0. You remember we have Auger, recombination, impact ionization, optical, whatever. All of this goes to 0. We don't have it. So the two continuity equations in steady state for Jp and Jn become those that you can see there. Derivative of Jp with respect to x is equal to minus q times u. And similarly, the derivative of Jn with respect to x is equal to plus q times u, okay? We can formally integrate these two equations over any domain, okay? So if you take one value of x that we call a, and another value of x that we call b, we can easily integrate the two equations from a to b. So for the electrons, that are those in the second line, we obtain Jn at b minus Jn at a equal to the integral between a and b of q times u. This expression is useful, although we are not able to calculate the integral, because you remember u depends on the concentrations. And the concentrations so far are not known. Their dependence on x is not found yet, so we cannot do the integrals, okay? But formally we can do them. We can take these expressions, okay? For the holes, you have a minus sign, so you have Jp at A minus Jp at B is equal to the same integral, okay? Now, how do we select the points A and B? We select them at the edges of the space charge region, okay? So we specialize the two expressions by letting B equal to O plus, A equal to O minus. So we obtain, if you look at the middle of the page, that the integral becomes the integral between O minus and O plus. The integral of Q times U, okay? Obviously, this integral is a current density, okay, by construction. So we can give it a name, as the mathematicians do. When we don't know how to deal with some term in the equations, we give it a name, okay? So Ju is the name of that integral. We don't know its value. Ju is also called the recombination current density, okay? And the recombination current density may be given two expressions, okay? Because if we integrate Jp, it is equal to Jp of O minus Jp of O plus. Conversely, if we integrate Jn, it is equal to Jn of O plus minus Jn of O minus, okay? Now we have to combine these expressions, okay? If you go back on top of the page, okay, you remember the total current J, that is some constant that we want to calculate, is equal to the sum of Jp plus Jn at any position. So let's take, for X, let's take O minus. Remember, O minus is the left edge of the space charge region, so it is the edge between the space charge region and the P region of the device. Okay. So if you look, if you select X equal to O minus, you have the J. You see it in the middle of the page. Can be written as Jp of O minus plus Jn of O minus, because we calculate them in the same place. But at this point, we may decide to replace Jn of O minus using the integral Ju. Okay, so immediately you find that it is equal to that Jn of O minus is equal to Jn of O plus minus Ju. Okay. Why did we go through this manipulation? Because if you look at this line, you have that Jp of O minus is on the P side, so where the holes are the majority carriers. And Jn of O plus is on the right, in the N zone, where the electrons are the majority carriers. So the line in which you see the parentheses on the right with MAJ, okay, that stands for majority carriers, we are able to express the total current density in terms of the majority carriers only, calculated at the edges of the space charge region. Okay. We can also do the opposite. If you look at the second line, we have, for instance, we start with calculating J at O plus, and then we replace Jn of O plus with Jn of O minus plus Ju. In this case, Jp is calculated in O plus, that is in the N region, so the holes are the minority carriers. And similarly, Jn is calculated at O minus, that is in the P region. Again, Jn is a minority carrier current, okay? So we have an alternative expression in which J can be expressed in terms of the current densities of the minority carriers calculated at specific positions in the device, okay? The second expression is preferable because of some properties that we shall discuss now, and some of them you already know from previous lessons, okay? Now we introduce the hypothesis of weak injection. You remember the weak injection condition is the condition in which the actual concentration of the electrons and holes depart from the equilibrium values little with respect to the majority carrier concentration. Okay. What is the importance of the weak injection condition? The importance is that if we are in the weak injection condition, then we can simplify very much the form of the net recombination term, because you remember it depends only on the minority carrier concentration. Okay. So if we take the hypothesis of weak injection, we can say that in the neutral region of p-type, that is, as you see there, on the left of O minus, we can simplify the net recombination term as n minus np0 over tau n. Tau n, you remember, is the lifetime of the electrons that are the minority carriers in this case. Similarly, when we are in the neutral region of n-type, that is for x larger than the position of O+, then we can approximate U as P minus Pn0 over tau P. Why is this so important? Because it decouples the continuity equations, okay? After introducing this simplification that is extremely important, the continuity equation for the electrons is derivative of Jn over dx equal to cube times n minus np0 over tau n. So it depends only on n, on the minority carriers, okay? Similarly, in the neutral region on the right of the n-type, the continuity equation for the minority carriers, that are in this case the holes, is also decoupled because it depends only on Jp and P. So this is the fundamental advantage of using the minority carriers in the analysis of the p-n junction, okay? You may argue that sometimes we may not be in the condition of using the weak injection condition. Actually, the theory that we can extract from this consideration is quite good, okay? So it applies to a large range of operating conditions of the device, okay? So we shall now proceed by solving the continuity equation for the minority carriers in the neutral region, because in such regions we can apply the simplifications that are discussed in this page. Of course, there is a price to pay, that we shall be able to find the electrons only in the neutral region on the left, and then we shall be able to find the behavior of the holes only in the neutral region on the right. And then somehow we shall be forced to put these two regions together, okay? But this can be done, so we shall see it. So for the moment, we have to solve the continuity equations, and of course, we have to couple them with the transport equation of the electrons or holes, okay? So let's go to the next. We jump over because okay. We are now in the neutral region of the p-type, that is on the left of O-. We have to solve the equation for the electrons, that is this one, derivative of Jn with respect to x equal to q n minus np0 over tau n. This equation must be solved between the left contact and the abscissa of O-, in the neutral region of the p-type. Of course, this equation by itself is insufficient because there are two unknowns. One is n and the other is Jn. So now we must couple this equation with the transport equation for the electrons. And you remember the transport equation for the electrons is of the drift diffusion type. So you find it here on the top line of this page in one dimension. So it used to be Q mu n electric field, but the electric field, you remember, is minus the gradient of the electric potential, and the gradient in one dimension is the derivative with respect to x. Then we have the diffusion term, that is Q times the diffusion coefficient times the derivative of n with respect to x, okay? So you see this equation, of course, contains the electric potential. So it couples this equation and the corresponding continuity equation with the Poisson equation. However, in this very case of the p-n junction, we can introduce another simplification. And this simplification that can be demonstrated, we don't have time to do it now, we shall do it later. The simplification is this. When we consider the minority carriers in a neutral region, so now we are in the neutral region of the p-type, so the minority carriers are the electrons, okay? So the transport equation for the minority carriers in a neutral region is such that the diffusive term is dominating, is much larger than the drift term, okay? So the approximation, remember, it applies only to the minority carriers and only in the quasi-neutral region, okay? So we can approximate the expression of Jn as a purely diffusive current density. So like Qdn derivative of n with respect to x. This is a very important simplification because since the electric potential does not appear anymore, it is not necessary anymore to solve the Poisson equation, okay? So we have eliminated also the Poisson equation, okay? So now we have Jn that is approximately equal to Q dn over dx. And then 2 pages earlier, we had the continuity equation for the electrons in the p region, that is this one, okay? So we put these two equations together. So that we have the net recombination term approximated with the weak injection condition equal, you remember, to the derivative of Jn with respect to x. Then we take the derivative of Jn with respect to x from the previous equation, okay? Of course, Q is a constant. Then we have the derivative of d times derivative again of n with respect to x, okay? The question is, does the diffusion coefficient depend on position? So can we take it out of the derivative? Yes, we can, because you remember the diffusion coefficient is proportional to the mobility. The mobility is influenced by temperature, but in this case, temperature is a constant, does not depend on position. Then mobility is influenced by the concentration of dopants, but in this case, we are in a neutral region of one type in which the dopant is a constant. And finally, the mobility is influenced by the presence of interfaces, but here there are no interfaces because the transport in a bipolar, in a PN junction, occurs far from the boundaries, okay? So we can just take d out of the derivative, and we conclude that this becomes equal to q dn second derivative of n with respect to x. Then we eliminate the charge, q here and q there are dropped, and we divide by the constant dn. So we bring dn in the denominator and multiply it by tau n. Well, then you remember, tau n is a lifetime, so it is a time. The diffusion coefficient is an area over a time. So the product tau n times dn is an area. The square root of it is a length. So we define a length, Ln, that takes the name of diffusion length of the electrons in the p region. And this is equal to square root of tau n times dn, okay? In the equation, we don't have the square root, we have dn times dn. So we have like the square of ln in the denominator, okay? And finally, in the derivative, instead of taking n, we can take n minus np0 because np0 is a constant, so the derivative will kill it, okay? In conclusion, when we consider the minority carriers in the neutral region, in a neutral region, so in this case the p region, okay, we are able to reduce the problem to the solution of a single second order equation that you can see here. It is a second order equation with constant coefficients, okay? Now we need, of course, since we have an equation of the second order, we need two boundary conditions, okay? And where are they? Remember, we are solving in the neutral region of the p-type, okay? Here, we are solving in this region, okay? So, or here. So, the boundary condition that we need are the boundaries of this region. One is minus infinity, practically minus infinity, because the contact is very far, okay? So we assume that when we go away from the junction, the semiconductor concentrations will behave like in equilibrium, okay? And the other boundary is O minus, okay? So we need to know somehow the concentration N at O minus and at minus infinity. These are the two boundary conditions that are necessary for this problem. Now we can observe that in all these calculations where we have derived the equation, it was never necessary to prescribe the position of the origin of the reference. Of course, we assume that the origin is in the junction, okay? But it is easy to understand that if we repeat all the reasoning that we have done so far, after changing the position of the origin, the current will not change, okay? The current that we eventually find after all these calculations cannot depend on the position of the origin, okay? So it is legitimate to select the position of the origin where it is most convenient, okay? And at this moment, we place the origin at O minus, okay? So for this calculation, we place the origin at O minus. So the meaning of x of O minus equal to 0 is, at this point, we decide that the position in which x is 0 corresponds to the point O minus in the material, okay? It can be demonstrated, and we shall do it, but not today, that the boundary condition at O minus, that at this point we can also indicate with the boundary condition n at 0, is equal to NP0. You remember NP0 is the asymptotic concentration of the minority carriers in the P region times the exponential of QV over KT, in which V is the applied bias. That can be positive or negative, doesn't matter, okay? This relation is not obvious. It's something that we must calculate later, okay? It takes the name of Shockley boundary condition. The other boundary condition is easier because at minus infinity, we are far away from the junction. So the semiconductor is uniform. We are in a uniform P region. So of course, the concentration N at minus infinity is NP0, okay? Conclusion, we have a second order differential equation, linear with constant coefficients. And we have two boundary conditions, okay? So we now can solve the equation. Obviously, the solution is a linear combination of exponentials. We are here. So remember, we are in the p-type neutral region. We are on the left of O minus. And we have set the 0 of the reference at O minus. The solution of the equation is that, you remember, the unknown function of this differential equation is n minus np0. So this is the actual unknown. So this unknown is a linear combination of exponentials with undetermined coefficients. So n minus np0 is this combination. So we can say that n is equal to np0 plus some coefficient to be determined times the exponential of x over the diffusion length plus Bn, that is another coefficient, times the exponential of minus x over Ln, okay? How do we find the coefficients? Using the boundary condition. So it is easy. If you take x and bring x to minus infinity, the exponential of x over Ln will go to 0, okay? The other exponential will diverge if you let x go to minus infinity, okay? Of course, this is unphysical. This is something that cannot be accepted because we cannot accept solutions that diverge. So the only way to prevent it from occurring is that Bn must be 0, okay? If you let Bn equal to 0 and then you put x to minus infinity, of course, you find n at minus infinity is equal to np0. So you have fulfilled the boundary condition on the left. Then you impose the boundary condition on the right. Remember, it is n at 0 it is equal to np0 exponential of qv over kt, okay? But you can calculate n at 0 also from the general solution. So n at 0 is np0 plus an, okay? You replace n of 0 here and you find an. So eventually, using the other boundary condition, you find that an is np0 times a quantity that we call f. It is dimensionless, okay? And this f is defined as exponential of qv over kt minus 1, okay? So you have Bn is 0, An is now calculated. It's completely known because we know everything here, okay? An is np0 times f, okay? What shall we do next? Well, you remember in the neutral region, the minority carrier's current is diffusive. So the expression of the current, Jn, in the neutral region of the p-type is equal to the diffusive term only. So it is q dn derivative of n with respect to x. But now we know n. N is something that we know. So we simply take the derivative of this expression of n. So we have q dn that is already there. This is a constant, so it disappears in the derivative. An is np0f, np0f. And then the derivative of the exponential is the exponential divided by ln. So this is the expression of the current at each point in the neutral region of the p-type. We actually don't need all the positions because you remember we need only one place, okay? And this place is O minus. We shall go back to some other slide in a second, okay? So O minus now is the place where we have set the origin, okay? So if you put x equal to 0 here, you actually find Jn in the origin, that is Jn of O minus. But if you put x equal to 0, what is left is this. So all these coefficients here, q, dn, np0 over ln times f is Jn of O minus. Okay? You remember where we need it? When we started, we said we are going to use the minority carriers. Here. We are using this expression, and we have just found Jn of O minus. Okay? Now the trick is clear, okay? We simply go on the other side, we go to the neutral region of the n-type, and using a similar analysis, we find Jp of O+. How do we do it? Well, we start with the continuity equation for the holes in the n-type neutral region. Then we must consider the expression of the diffusion current density for the holes, this one. And again, we neglect the drift term because the minority carriers in the neutral region have a transfer mechanism in which diffusion dominates. Okay, so you remember for the holes, diffusion as a minus, we have minus q dp over dx. But we have another minus in the continuity equation here. So this minus will compensate for the other minus. So we have the continuity equation, then we have to calculate the derivative of Jp. We do it using the previous line. And using similar definitions as we did for the electrons, we have a second order differential equation for the excess concentration of the holes with respect to equilibrium. All the minus signs have gone. We define the minority carrier diffusion length as the square root of tau p times dp. At this point, we observe that the neutral region of the n-type goes from O plus to plus infinity. At this point, we decide for this specific calculation to place the origin of the reference in O plus. So we say x over O plus is the new zero. P at 0, again, due to the Shockley boundary conditions, is Pn0 exponential of QV kT. P at infinity is the typical P of a neutral region of n-type, okay? So we have the two boundary conditions. The procedure for solving the equation is just the same. It is here. In the n-type neutral region, P is equal to Pn0 plus a linear combination of exponentials. In this case, you see the minus, just for convenience, we have placed the exponential with the minus first and that with the plus second. So again, we have Bp equal to 0 because of the asymptotic condition. P at 0 is equal to the Shockley boundary condition. So AP is equal to Pn0 times F. F is the same as before, the same F as for the electrons, okay? And finally, we calculate the current, and then we observe that all this quantity here, the coefficient, is equal to Jp at O plus. You notice it is really unimportant where the origin is, because eventually what we want to calculate is this coefficient here, okay? So now we have Jp of O plus. We go back. And we have JP of O plus. So we have almost finished, because we have calculated J as the sum of JP of O plus that we know, plus Jn of O minus that we know, plus Ju still to be found. Okay. Of course, we have introduced some approximations and some concepts that are left unexplained. So we must explain tomorrow. Number one, why is the diffusive term in the current density of the minority carriers dominant with respect to the drift term in a neutral region? That was taken as granted, but we shall explain why. And the second thing that must be demonstrated is the Shockley boundary conditions that we took for granted, but they also must be demonstrated. Okay, but we are almost at the conclusion, because we have calculated the two major ingredients of the current density in the PN junction. Okay, I think that we should stop here. There are still 2 minutes left, so if there are questions, you can ask them now. If not, we shall meet each other again tomorrow. And so we stop for the moment.